part A, the XX stress is 5 times 10 to the 8. The XY stress is 8 times 10 to the 7. The XZ stress is negative 5 times 10 to the 8. And now go up to the Y face. You have 8 times 10 to the 7 in the X direction, and the other two are zeros. And then the Z face, in the Z direction you have negative 2 times 10 to the 8. In the X direction you have negative 5 times 10 to the 8, and then 0 in the Y direction. Right? Yeah. Nope. There's not much to this, but still it takes a while to, kind of ingrain it. But and then if you're going in this direction, look back and make sure it's symmetric, because something went wrong if the matrix isn't symmetric. So XY and YX are the same. XZ and ZX are the same. The other ones are zeros, so it's symmetric. And then for the Voigt notation, there's XX, YY, ZZ, and now YZ is 0, XZ is negative 5 times 10 to the 8, and XY is 8 times 10 to the 7. Any questions about that? And then you should be comfortable going the other way too. So if you have a matrix 4 times 10 to the 8th, 0, well, actually, let me do one like this. 1.5 times 10 to the 8th in the ZZ direction. What's the stress cube? So in this case, we just have two normal stresses, no shear stresses. So in the positive X direction, we have 4 times 10 to the 8th. In the Z direction, we have 1.5 times 10 to the 8th. And a stress state like this would be called biaxial tension. And you would get a stress state like this. I mean, you can imagine what's going on here is the positive X and negative X faces are being pulled apart. At the same time, the positive Z and negative Z faces are being pulled apart. So along two axes, you're applying tension to this cube. Okay? Any questions about definitions of stress? So that's all there is to defining the stress. And as you can imagine, now what we're going to be concerned with for most of the class is figuring out how to go from external loads to figuring out what these stress values are, So just, we're done defining it, but that doesn't say that we know how to calculate it yet. But now let's go through defining strain. remember that for the materials we're dealing with, there's a linear relationship between the stress that we just defined and the strain. And that's called Hooke's law, even though we're talking about a matrix relationship instead of just a constant scalar relationship. So Hooke's law says there's a linear and linear means, in other words, a constant matrix relationship. Yeah, right. There's like a matrix constant of proportionality between the stress and the strain. Between stress and strain. In general, what starts as an infinitesimal cube is deformed by loading into a parallelepiped. So you start out with your stress cube, and it's deformed into something with parallel faces like this. Okay, so angles can change, lengths can change, but the faces have to stay parallel to each other. Length changes are referred to as normal strains. And angle changes are referred to as shear strains. The normal strains are EXX, EYY, and EZZ. And the shear strains are gamma XY, gamma XZ, and gamma YZ. And notice that in my picture, so my drawing shows big length changes and big angle changes. But remember that one of our key assumptions in this class is small strain, small deformation. So something like this is not something that we're going to analyze in this class. We're talking about things well under 1% in most cases as far as the change in length. So one of our key assumptions in this class is small deformations. So these strain values are always going to be really small. The stress values, remember, are going to be big. They're going to be, you know, something times 10 to the 6, something times 10 to the 8. These are going to be something times 10 to the minus 4, something times 10 to the minus 6, little tiny values like that. Okay, so let's see. Let me just define normal strains. So the mathematical definition of the normal strains so let's say that this is just direct head-on view of the XY plane. And this is before the deformation. So let's say that this length is capital L0, and it's a cube, so this one will also be capital L0. And after the deformation, you have different values. Again, I'm drawing these to look like big deformations, but we can't, we're not going to deal with materials and loading where that happens. But after the deformation, you have a value Ly on this side and a value Lx on this side. Then the normal strain Exx is equal to Lx minus L0. So the change in the length divided by the initial length. Or you can think of it as the deformation in the x direction divided by the initial length. The other definitions are similar. Eyy is equal to Ly minus L0 over L0. And EZZ is equal to LZ minus L0 over L0. And notice that with this definition, if you get a positive value for one of these normal strains, is the length increasing or decreasing? Yep, the length has to be increasing to get a positive value. It has to be decreasing to get a negative value. And look back at the definition of these normal stresses. If you have a positive normal stress, is the element in tension or compression? Yep, positive normal stresses are tension, negative normal stresses are compression. So in that sense, the sign convention matches for the stress and the strain, okay? If something's in tension, it has a positive normal stress, and the result will be a positive normal strain, okay? If something's in compression, then they'll both be negative. So a positive normal strain is stretched. A negative normal strain is contracted. And the sign, let's say the sign convention matches the signs for normal stress. Question? No. Any questions? Okay, that's it for today. So next time we'll talk about shear strains, and then we'll talk about that relationship, that linear relationship between the stresses and strains. Okay.